Okay, so let me start, and I promised to say something about flag manifolds and so on. Well, but so let me first just connect it with semi-infinite type constructions, which we talked about. Well, and I explained that if we have algebra is the generator, so it is sum of I z minus I, and EI commutative algebra, and such E satisfy the relation EZ square equals 0, that I hope I explained that such kind of algebra E, it has a representation of special kind, even two representations of special kind, which are has great similarity with semi-infinite exterior power. Namely, what I said actually, that such kind of algebra has two representations, and basis in this representation, it is what? It is, we have to draw one-dimensional lattice. Configuration here is collection of crosses which stabilize to a dense tail like that, and this dense tail in this direction, it can go by odd or even numbers. It can be something like, for example, if it is even, it may be to n plus 2 to n plus 4 and so on. And n is something, but what is important is that it is some kind of dense parking, or how to say it, in this direction, and it is 0 in this direction, and each configuration of such sort like this, for example, 0 unto maybe 0 here, 1, 2, 3, 4, 6, and so on. For example, such configuration, we have just infinite monomial, like E0, E4, E6, and so on, and such kind of product, of infinite product. We can understand this as some special, as a monomial, in some sense, in a ring of polynomial of an infinite number of variables. Anyway, I claim that it is some space. In this case, it is W even because tail has such structure. Yes, and we know, at least I announced, that on this space we have the action of my algebra EI, and also this relation is also hold, so it is representation. Even more, I said that such kind of space is irreducible representation of two Z semi-direct of EI, while Z is shift operator. And 2, it means that in Z, generators of Z conjugate E and shifted by 1, and it is shifted by 2. 2 is because our tail is going by this way. Anyway, I have this space, W even, and in this space I have a collection of special vectors, which are appear several times in my talk, and such vectors are extremal vectors. And for example, it is E0, E2, E4, and so on, or E minus 2, E0, E2, and so on. And let us denote this vector by V0, this V minus 2, and it will also V2, and so on. Yes, and what else is true? I wanted to consider this EI as generators of commutative Lie algebra, and no, if it is Lie algebra, then corresponding abelian group is acting. Now, first of all, if you look carefully to the structure of this space, you will see that these operators EI are acting by a nilpotent way. So it means if you take any vector, you can find some number n such EI n is 0. N is dependent on choice of vector in I, but it is 0 for some choice of n. And because of that, the exponent of TEI is well-defined operator on this space, and we can generate the group by all this TEI, and so some kind of abelian group, maybe A, is acting here. Yes, and after that I can do the following. I can take the extremal vector, which is something like that. This is let us follow such notation. This will be Lie algebra, and for example, A capital will be corresponding group. So it's Lie algebra with the basis EI, and this is the group generated by exponent of TEI. Yes, and well, and now I have my vector space. It is W even, and I have here the vector. I can take projectization of this W, just space of all lines in this vector space, and what I can do, I can take this vector and just act by this group. And what does it mean? That if I have, for example, W0 is this, then this vector itself is killing by E0, E1, E2, and even by E minus 1. So I can take V0 and let me understand it as not vector, but point of the corresponding space. And then I can exponent T, and first element is E minus 2, and it is T1. Yes, and it is not a big deal because E2 some power, in this case it is maybe 3 zeros, so just in a projective space I have point which is corresponding with 0, and it gives me the line. And if T1 goes to infinity, then I can take closure of this line, and it gives me CP1, which is living in this projectivization. After that, I can take exponent. Maybe let me put 2 here. T3, E minus 3, and I can act on this line, and it gives me something like that. And it is orbits of this action. I also can take a closure, and then I can continue, and it gives me some manifold. I first act by E minus 2, then E minus 3, then E minus 4, and so on. And then if I act by E minus 2, E minus 3, and so on till E minus m, for example, then it gives, and I consider the orbit and take closure, and it gives me singular, yes, but finite dimensional manifold. But after that, m go to infinity. As a result, what I get we will have inductive limit of finite dimensional manifold. Yes, and anyway, it will be something. But after that, no, it is V0, yes, but then I can go to V2. And it will be bigger manifold, but well, because of the action of this Z to Z is acting on the algebra, and actually it is acting inside my representation just by shifting for these monomials. So construction now is going on by which way? First, I construct what I did till this moment. I take with 0 and act by corresponding group. My group is A, and take closure, and it is some manifold. Well, but after that, I act to this manifold by Z, by such a shift. So I can move it by 1, by 2, by 4, and so on. And after that, I get something which can be understood as an injective and projective limits. So first, I considering, or no, it is like that. So first no, it depends, but first I construct some manifold as inductive limit of just making this number n larger. But after that, I considering bigger manifold, I can start from V0, but I can start from V2. And it gives me bigger manifold. I can start from V4, and it is also give me a bigger manifold. And so after that, I have some collection of manifolds and also some inductive limit of them. Altogether, it gives me something, and this something is no, it's constructing by some way, this way, but it is some infinite dimensional algebraic manifold, and this infinite dimensional algebraic manifold, it is just the Grassmannian for SL2 hat, and from the point of view of standard logic, how we construct Grassmannian, it is so I have not the group no how to say what actually is finite dimensional counterpart of this. If I have some finite dimensional, no, even not without hat, some finite dimensional algebra G, say SLN, and I take finite dimensional representation W of this irreducible, and V is highest weight vector, and V alpha external vectors. And about these external vectors, for generic highest weight, they are labeled by Weyl group, and if you define the flag manifold, for example, how you can do it? You can take productivization of W, you take vector which is corresponding to highest weight vector, and you're acting by group here, and it will be just flag manifold. Or you can do the following. You can take external vector W alpha, and you can act by nilpotent group from G. You get some submanifold here, and after that you can consider the manifold which contain all of them. So just take union of all these submanifolds, and it gives you the construction of flag manifolds. And this is what I'm doing here in the infinite dimensional case. Okay, now what I am talking can be done in more general case, but before. In this case, let us take this V0 and let me do what I said. So I mean, I can take exponent of T2 e minus 2, exponent of T minus 3 e minus 3, and let us go till T minus n e minus n, and we have some collection of points for productivization of my representation, and it gives me some cell, actually, at least something which we have coordinates T2, T3, and so on, Tn. And after that, I can make up a closure. Closure, it will be finite dimensional manifold, and dimension of this finite dimensional manifold, surely how many t's we have here, because it is closure, and it is n minus 2 in this case. Yes, and I want to say that such kind of closure, it is nice algebraic manifold, singular, yes, but it will be a Schubert variety for group SL2 hat, and so we construct it by this way.
So here the order in which you take this exponential is important, right?
No, in this case not, but because I consider only the simplest possible case when all E are commuting, yeah, and so on. But if you go to next case, even SL3, then yes. In this case, yes. Anyway, I want to make up two comments. One comment that from the point of view of the space W even, maybe it is good to have in a mind the following picture, that because I said about two gradings, and so these gradings are what? That we have extremal vector, for example, which end by E2. And then if I act by E0, I get also extremal vector. And because of what I called Q grading, this part is living in the top of my space. Then we have E2 here, then we have E minus 2 here, then I have E4 here, then I have E minus 4 here, and this is so on. And I draw these dots and arrows just because it shows the structure of the space. So extremal vectors are here are dots, and the E how we go from one extremal vector to other extremal vectors. Yes, and I draw it by this way that on all space we have what I said Q grading. This is top, and this, for example, part is living 2 floors down, and here is 4 floors down, and so on. Yes, and we also have Z grading. Z grading is this one. Yes, because as I said, E add Z grading by 1, so I do not fix precisely what is Z grading. It is possible, but at least here some Z grading, this is +1, and here is -1, and so on. And this is the standard story, that weight diagram of my representation. Weight diagram, it means what degrees in Q and Z gives me non-trivial, corresponding to non-trivial elements, and in this case, corresponding non-trivial grading in my representation, they are concentrated inside this parabola. Well, and now what I said about let us considering a little bit what we have here. I have this point, and I can act by E0, suppose only, then I get this two-dimensional space. No, in principle, I can act by all non-negative I to this vector, but positive I give 0, it gives me this two-dimensional space. Then I can take, for example, this vector. And suppose I want to act by E0, E1, E2, and so on. No, first of all, what we see, that to this vector, according to this weight diagram, I can act by E0, I can act by E1, I can act by E2, and all other E, starting from this acting by 0, and actually this follows from this picture. So, but if I act only by this, then I act by E0, and E0 is acting by this way. E1, for example, acting by this way. And also, if I consider just subspace, which acting from, which generate by this vector, and I act by, actually by this 3, then what I get, it will be this, I can get 3 vector. Here is 0, E1, E2, and it is also easy to see that I have 3 vector here, and I can get 1 vector here. Yes, and you see, and it is typical situation which appear in such cases, that I have semi-infinite space, I act by elements, in this case, by this part, to external vector, and as a result, I get 8-dimensional space. You see it. And the character of this 8-dimensional space, it is, no, it depends how to write it. If we start from this, for example, it will be 1. Here it is Z. It will be 1 plus Q inverse plus Q. It is these 3 vectors. Then it will be Z squared. 1 minus Q minus 1 plus Q minus 2. And then it will be again Z cubed. Yes, and the point is that 8 is 2 cube, so it is looking like C2 times C2 times C2. And if Q equal 1, then these things will be 1 plus 3Z plus 3Z squared plus 1, and it is just a character of C2 times C2 times C2, but all things is ZQ character of such product, this times this times this. And this phenomena is appear very often, and in this case, well, and by the way, because I promise some connection with link invariants or not invariants, but actually what I have one more lecture tomorrow, and I want to concentrate all this business yesterday. It can't be understandable at all, but at least I do it tomorrow. But now I want to say that such kind of expression appear as some even precise. This is possible, but I'm not precisely know what kind of link you have to take. But similar expression appear as a link invariance and so on. It is one thing, and other things is what? That it is my space. And as I said, operators suppose E0, E1, and E2 is acting here. And I can take this vector and act by corresponding group. And this group act on projective space, and what I can do, I can take first exponent by this, then exponent by this, then exponent by this. So I make orbit of these one parameter subgroups, and then make a closure. And it gives me 3-dimensional, after closure, it gives me 3-dimensional compact manifold, which is some submanifold in the projective space. And this subspace actually can be understood in terms of this manifold. Now, this manifold is 3-dimensional manifold, and it is Schubert variety, 3-dimensional Schubert variety, and because it is subspace here on this Schubert variety, we have some linear bundle Xi, and sections of this Xi is dual space to this. It is 8-dimensional subspace. So well, and it means that I have this, I have this, and no, this is 8-dimensional space. And by the way, in this case, because we have such kind of algebraic geometry interpretation of this space, we can try to write down the Lefschetz fixed point formula. And it will be something, not what I wrote here yesterday, because it is different space. But nevertheless, it is similar. But what I want to say now that, well, it is some sort of geometric interpretation of Lefschetz fixed point formula. What really I explained yesterday, I want to say a little bit later, but no, again, my time is restricted, but nevertheless, I want to present my one of my favorite example. Yes, and this example, it will be the following. Well, and it is also concerning the question which I only mentioned about lattice vertex operator algebra. No, I can construct some manifolds, and these manifolds in some cases coincide with affine Grassmannian, but my constructions of such kind give me possibility to construct much more, many examples of the manifolds. And in this example, let me explain. Okay, suppose example. I want first what I want to do, to construct semi-infinite space. But for the semi-infinite space, in a simplest case, surely I need what? I need to take EZ, and in examples it can be commutative or skew commutative, or suppose commutative, and I considering the case when it is EZ square equals 0, and then make up some vector space where such EZ is acting. But as I said, such kind of strategy, I can vary these relations. And because it is commutative, it means that suppose I want to deal only with quadratic relations. And this is surely quadratic relation, well, but I can add more quadratic relations. And more quadratic relation is simplest things is square is 0. And I want to work with relations like this and that. Yes, and first of all, what does it mean? Ez is the sum of ei z minus I, and this relation means that the sum of e alpha e beta is 0 when alpha plus beta equal, say, any I. Well, but I want to add this relation, and this is derivative. But what does it mean? It means that I have this relation, but I have one more relation. And because it is derivative, it means that I have to write the sum of e alpha e beta, here alpha times beta, alpha plus beta equal I, and it has to equal 0. And it does not matter what I understand by derivative. It can be d over dz or z over just this or this. It is not no difference, but from the point of view of component, if you are working with these two derivatives, that it means you are talking about generated by E alpha, and this is the relations. Fine, and but from the point of view, now logic is the following. First, what I have to do, I have to take some vector. Suppose that such. Anyway, I want to find something as the space of W even. Does not matter. Later we will see what does it mean in this case. But at least I want that it will be something similar to semi-infinite space of forms. So what does it mean? It has Q grading, which is restricted from one side, and operators E, I is acting here. These two relations are held, and not only that, we want that Z or Z times some number, it actually before in this case, also acting here. This is I want that this semi-direct product to EI is acting on this representation. It is what I said, it is just that it's similar to what I had there. Anyway, to starting point to do this is following. I wanted to have some V. It will be external vector in my future space. And I want this external vector is killing by E0. E0 may be 1, E2, and so on. And after that, what generated by this vector is C, E minus 1, E minus 2, and I factorize it by consequence of these relations. And what we see, that using this, we can, in monomial, if I have something EI square, I can rewrite it. And if I have something EI plus 1, I also can rewrite. But for that I used only this relation. But now I want to use this also. For that I can see that EI plus 2 can be, I can rewrite it also, and EI plus 3 also. Yes, so after that, the natural conjecture, because I can do it, that after I take this polynomial ring and factorize it by quadratic relation, which follows from this, that the basis in this space, it will be what? It will be EI1, EI2, EI3, and so on. And now the distance between these i's is bigger than this. So it can be, for example, E minus 1, then E minus 5, E minus 9, and so on. And they cannot be closure. So it's some kind of repulsion, and how to say it, by this way. Yes, and again, it is simpler, but also not evident in such kind of case that, well, such kind of monomials give me really the basis in this quotient. It's okay, and if you want to proceed or to make up this construction in this semi-infinite manner, then as a result you get the following things. That we can construct the representation of such kind of EI, which in this case is one of the simplest one, but nevertheless we want that such kind of relations are held. And in representation we have basis which is labeled by configuration, and configuration is we have 0, minus 1, minus 2, minus 3, and so on. And we have to put crosses. And these crosses cannot be near each other. So the distance between these crosses can be 4 or more than that. 4 plus something. Plus 0, plus 1, plus so on. It cannot be in a distance 3. Yes, and so it is also something like Fibonacci condition, but just distance between the crosses are bigger than this. And the statement is that no, you can expect, but the fact is that it is really true, that we have 4 different representations of my algebra EI, and they are labeled by type of a tail. Tail can be surely like 1, 4, 8, or 1, 5, 9, and 2, 6, and so on. It is, but we are interested in this part. So tail is going on by a sequence, and there are 4 types of tails. Yes, and I want to say that we have as a result 4 representations of algebra EI. Now, the people who know about their representation of lattice vertex operator algebra, they can say that we are just living in this situation. So if we have one-dimensional lattice vertex operator algebra such that corresponding lattice is square of vector, generating vector of this lattice is equal 4, then the corresponding lattice vertex operator algebra has 4 representations. And what we really did we constructed 4 representation of this vertex operator algebra. And again, it is interesting things, but what I want to say that in a case if you have generic lattice vertex operator algebra, at least with the positive quadratic form, then you can repeat some kind of construction or like this, even if lattice has dimension bigger than 1, and construct the representation by this way. But what I want to say, well, let us consider, for example, some case that I have a vector, and suppose what is this? I act here external vector, I act here by E0, but next one it has to be now E minus 4 in this case. And here we have E4, and here we have E8, and here we have E minus 8. And in this case, it is the same structure which I explained before, but in some sense 2 replaced by 4. And we have some representation. In this case, it will be a representation of vertex operator algebra. But again, all admissible weights which we have, they concentrated inside some parabola, but this parabola will be now like that. Okay, but question which we have here now is following. Well, I want to take this vector, for example, and we get as a result no, well, how to say? Now question. I have this representation, and so it is just some infinite dimensional vector space, which is W. Maybe let us put 0 here. This is one of the 4 possible representation of my algebra. Again, I am saying that operators EI are acting here, and no, we do not know that nothing like group SL2 is acting here, but at least Lie algebra which generated by EI, A is acting here and corresponding group is acting here. After that, why not try to do the same things? So just to take external vector, act by considering the orbit of the corresponding group of the projective space, take the closure and just ask what kind of manifold we get after that. And I formulate such kind of question just because I think the answer is completely unknown. That well, and from geometric point of view, if we do not have this, then we are talking about the Schubert varieties for Grassmannian. That is a lot of things is known. For example, Satake correspondence, we know McPherson cohomology of corresponding manifolds, and so a lot of things are known. But in this case, to be honest, nothing is known at all. And if no, here it is not good place to make exercises right now, but nevertheless, what is going on? I take, for example, this vector, and then I act by E0, and it is acting by this way. And here we have also, it is 4, so it is 5 vectors here, and 5 vectors here. And so before in 2 we have 1 plus 3 plus 3 plus 1. And here it is one more here. Here we have 1 plus 5 plus 5 plus 1. It is like this, it has dimension 12, and such kind of corresponding manifold. No, surely it is singular, but it is always singular. It has dimension 5, and it has linear bundles there, and it is some line bundle sections and so on. Yes, and maybe not, I will try to formulate a little bit later some kind of conjectures, but right now only the question. Question is what? That in this special situation, we can determine the orbits of all external vectors there and define some analog of Grassmannian for SL2 hat, which, as I explained, appear if we do not have this. Then question right now is only what is this? And it is some interesting manifold, and it is extremely good at least have to any possible information about this. Now, maybe next, what I want to say today is Schubert varieties and what I said, graded tensor product. No, actually it is the same story, but what I want to say, something about the construction of fusion. And now this construction is going on by the following way. Suppose I have Lie algebra with generators EI, and no, EI, usually I belong to Z, but right now it is not very important for me. But maybe it's okay. So if I is Z, that the corresponding space is C, Z and Z inverse. This is space with this basis and such that EI is equal ZI, something like that. Anyway, it is Lie algebra, where infinite dimensional, but the basis in this Lie algebra is labeled by ZI, so it is infinite dimensional. Well, now this Lie algebra, it has evaluation representation. No, actually, evaluation representation, this is something which is well known in SL2 case, but I do not want to work with SL2. Again, I'm working only with EI, which are corresponding to maximal nilpotent for this SL2, so I'm talking about representation of this. But at least evaluation representation of this is what? It is some vector space of dimension L, and it is sitting in some evaluation parameter U. And what is this? To determine this, let us say the following, that this Lie algebra, suppose it is, say, A, that universal enveloping of A, we can consider the map to C of some variable Z. And then this map is going on by the following. The operator EI, let us put T here. Operator element EI is going on in U power I times T. Yes, it is no evaluation, it is clear why, because it means that if we have this, if I have this ZI, I substitute in U, and it gives me this. And operator EU is going on to this. Yes, and if I want to have L-dimensional representation of this algebra, actually I send it to CT and here over T power L. And after that, I get some very simple representation of this algebra with basis 1 T square and so on, T L minus 1. It is L-dimensional representation where operator is depending in parameter U and representation EI is, they are acting by this way. Just product to UI times T. No, very simple things, and it is surely related to evaluation things. And so after that, if you consider the fusion, the standard approach to what is calling fusion business, this is what? You take this Lie algebra and you write down CL1 U1 times CL2 U2 and so on times C maybe some LS US. So it is tensor product of such kind of evaluation representation. Yes, and the fusion procedure is which one? So first one, if you take such kind of tensor product, then generic situation, it means that all UI are distinct. So UI does not equal to UJ. Now it is clear why, because if say U1 equal U2, it is very, from this point of tensor product, it is very generic things. About fusion procedure, it means what? That no, first of all, for that, it is better to work only the part of this, which we have only E0, E1, E2, E3, and so on. So suppose it's not necessary, but it will be easier for us now. And the EI is not Z, but Z plus. It is not negative. So I want to work only with this algebra, and I have this, and I fix U1, U2, and US. I fix L1, L2, and LS. They can be equal or distinct, it does not matter. And after that, I want to degenerate this representation in a sense to send all EI to 0. No, there are several ways to do it, but one way is following, that this commutative algebra is acting here. And by definition, on this tensor product, so each space is CT over TL1. Therefore, here we have highest weight vector, you can call it by any way, so it is 1 in a point U1 times 1 in a point U2 times 1 in a point US. And after that, such kind of commutative algebra is acting here. And this commutative algebra is universal enveloping of this, and it has no, because it is 0, 1, 2, and so on, and this algebra U has a grading U0 plus U1 plus U2 plus so on. This is just because this has grading 0, it has grading 1, it has grading 2, and so on. Yes, and no, this representation surely has not natural grading, which is compatible with this. But what we can do? We can take on this representation R, we can construct the filtration. R0 is, suppose this vector is W. R0 is U0 times W. What is U0? U0, it is C of E0, so it means I just take W and act by this. Next, R1 is U0 plus U1 acting to W. And U0 plus U1, what is this? I want elements of degree 1 here. So what it means? It means C E0 plus C E0 times E1. And so I act by this. R2 is U1, U0 plus U1 plus U2, and it applied to W. Anyway, I have such kind of filtration, and I can write down after that R0 plus R1 over R0 plus R2 over R1 and plus so on. And as a result, so such kind of business I can make up with any representation with a fixed cyclic vector, and this cyclic vector is this. And so after that, after such construction, I get something which will be graded representation of this. And so what I want to say is that if, for example, if you take 2 points, U1 and U2, and make up this, and doing this for C2 times C2, so it's 4-dimensional representation. So what we are doing, we take highest weight vector W, I take by E0, it gives me three vectors here, E0, E0 square, and so on, and there I act by E1, it gives me one more vector. So as a result, it gives me what is people usually calling the fusion procedure. No, the interesting things, which is in general is not proved, but in this case it is true. So if I have CL1 U1 times CL2 U2 and so on times CLS US, and if I make up this procedure, then I get some representation of the algebra E0, E1, E2, ES minus 1, first of all. I mean corresponding adjoint things. And also that the result does not depend of a choice U1, U2, and so on, US. The only, no, it is completely not evident, first of all, and second, if you vary a little bit the problem, that it is even not correct. But in this case, it is correct, that the result does not depend of a choice of U1, U2, and so on, US, and it gives me something which is calling the fusion of representation is SL2. For such construction, we do not need SL2 at all, but at least it will be, no, we get only E0, E1, E2, and so on, ES minus 1. If we need SL2, so we need H's, F, and so on, but I do not want to take care about them, it is just this. Yes, and one question is how much it is related with what I explained about this semi-infinite construction. One thing is following. Well, if I talking about only this case and take a semi-infinite space which is W0, then what? I just write down this picture again. The E0 is acting here, here is acting E1, E2, excuse me, here is acting E minus 2, and so on. Then I have, as I explained, and here it is more or less clear that I have this, and so on. I take this external vector, and as I said, I acting by E0, I acting by E minus 1, acting by E minus 2, and so it gives me 1, 3, 3, 1. And the point is that corresponding part is, no, because I use only E, this is a representation of algebra with generators E0, E1, and E2. Yes, and if we want to get, no, and it is bi-graded representation, so it has Z grading like this and Q grading like this. And if you want to get it by fusion construction, you have C2 in U1 times C2 in U2 times C2 in U3 here, and make up what I explained. So it means, well, we have here filtration and then go to the graded things. And the point is that what we can construct here and what we have here is just the same things. They can be identified now. It is maybe well understood more or less in this case why, but at first naive thing that it is just the same things. And no, the interesting question, and this question formulated long ago, but no answer till now, what the similar story is happening in this case. But before that, let me just say something about this. So, what is going on? I have represent space W0. And this W0, actually, surely I had no possibility to construct it by, at least in some sense, I explained that it can be constructed by this semi-infinite way. But even if we do not talk about the geometry, it is very different. No, from the first glance, very different way to construct the same space. Because what we see here, I have this vector, and then I act by, or suppose I act only by EI, where I is non-negative. Well, but at least if I act to this, it gives me this, and it is two-dimensional space C2. Fine. After that, I take this point and also act to this point by all positive E, and this positive E in this case are E0 and E1 and E2. And as a result, I get 8-dimensional space, which I claim, and it is really can be proved, that it is this tensor product, but we have to make these graded things, and standard notation is like this. Yes, and from the this guy is a representation of this algebra. This guy is also representation of this algebra, and you see here this is a map from this to that. And if you go to the further vector here, then you have C2, 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 C2 actually 5 times, and you make up this grading business, filtration grading business, and so on, and then you have a map like this. And then you are going like this, like this, like this, and so on. And as a result, after you're going off the inductive limit, you get all this space. So it is a very, very interesting and important phenomena which says that this space surely appear as a which I do not explain much, as a representation of SL2, and also it can be constructed by semi-infinite way, just using only relation easy square, and not only that, that we can play from the first glance very different game. We can take this, and so on, and considering the inductive limit of the corresponding spaces. And the result gives me the same story, the same space. Yes, and if here I can formulate this thing is precise statement, but if we want to formulate it non-precise way, so what is going on? That we have representation of SL2 hat in this k equal 1, and then we can take SL2 times CZ. We take evaluation representation C2 U1 times C2 U2, and so on, and so C2 US, and we can construct this representation by some inductive limit procedure when number of products become to infinity. But to do it, we need all this U collapse to one point and make up some other tricks. But anyway, this can be understood as, in some sense, of an infinite tensor product. And this is, no, such kind of story appear in representation of affine algebra very often. So we wanted to understand integrable representation as an infinite tensor product, and this is one way, at least, to formulate this precisely. Yes, and why I want to explain it, not in details, but at least something that the real story is that we can construct the representation of different vertex operator algebra using this fusion business. For example, if we take in this case, I deal with C2 times C2 times C2 many times. And I get, as a result, something, if I do all this, I get something where operator is acting and satisfies this condition. if I replace here 2 by 3 and try to do similar story, then I get also the semi-infinite business, but this replaced by E cube. And so this is going on by this way. And now, in some sense, it is also, no, it is all not new things, and even it is known what to do if to play with different dimensional manifolds, take tensor products, and so on. Yes, more interesting thing is what to do if we want to construct as a limit vertex operator algebra like this. And for that, I can only formulate rather old conjecture, but I think that this conjecture is interesting. And for that, we need to make, in principle, the same fusion business, but for a little bit more complicated representations. So what we can do? Suppose we take representation U1, U2, no, first not representation, but just point, U1, U2, U3, Un. Yes, and then from what I said before, we have C E0, E1, E2, and so on, and we have a map from this to C T1, T2, and so on, Tn. Yes, and the map is which one? The EI is going to the sum of Ti times U. No, here is some S, US power I. Now it is just evaluation map. Then my parameters U1, U2, and so US in the previous business and here right now also, suppose they are all different, but after that, what I can do? I can go from this to the quotient of CT1, T2, and so on, Tn, by some ideal. Yes, and in my previous consideration, what was this ideal? What was it? I took this ideal just generated by T1 L1, T2 L2, and so on, and Tn Ln, and it gives me the fusion construction of the tensor product of corresponding representation. But in principle, this ideal G can be arbitrary. No big, no, I can factorize it by arbitrary ideal. No, arbitrary maybe it's too much, but in principle I can do it well, and after that I have something, and in this something I have the same filtration, I have grading, and the question is, I have something with some interesting character, and what is this? Surely, in general, it is not. No. Now about questions. First question that surely we can done it. We can do it, but for what J? Suppose we are interested in a case when quotient is finite dimensional, but when we want to calculate the corresponding character, for what J it is possible to do. But a situation which appear, for example, in this case, is following, that T1L, T2L, and so on, it is the simplest version of a regular sequence. It is most simple things which in principle we can find. But the situation which appears here is following, that we need to take J, which is generated by T1 square, T2 square, and so on, and it is Tn square. But it is just what we had before. It was corresponding to the case when we had only this and had not this. But now we need a little bit more than that. We need T1, T2 is 0, T2, T3 is 0, and Tn minus 1, Tn is 0. Yes, and after that, correct? No, maybe yes. No, I wanted to formulate conjecture, and this conjecture, maybe it is. Well, it has to be true, but I need to adjust. Anyway, but here the question is what? I take ideal G is like that. I take this space. I make up this fusion construction. I get some graded representation of A0 and 1 and so on. And I want to say something about that. Yes. And yes, and I think at least that maybe it is that such kind of spaces appear if you want to describe representation of this lattice vertex operator algebra, that the corresponding pieces as representation of E appear by this way. And okay, conjecture is conjecture. I do not claim that it is true. I hope, but and I even do not claim that the state. No, I believe that statement it is something like that, but I do not see right now even this case that this 12-dimensional space is appear by this way. Right now it is, maybe I confuse some things, but something like that, this is correct. Anyway, the real story is from one hand side, we have representation of vertex operator algebra. From other hand, we have fusion type construction and representation of vertex operator algebra. I want to construct by the similar way as it is happening in this semi-infinite for EZ square. I mean this SSL2 case as the n is going to infinity, and I embed these spaces to each other, and in the end it gives me the desired representation, and so well, this is it. This no, I stop about this, but I want to say that for me it is a very old problem and important. If somebody will have some ideas, that I will be happy. Yes. Now. No, in my remaining time for today, first I want to say two things. One thing is following, that I maybe yesterday I formulated the statement of Zhenya Gorsky, and Gorsky statement, it was what? That in the Gorsky case, he took the toric knot or link, maybe not. Toric knot, it has two labeled by two numbers, n and m. And as Gorsky said, that as for any link, for this link, we have two things. One thing seems to be rather simple, and it is Jones invariant. And this Jones invariant, it is some polynomial nm in Q. And second thing, that it also have Khavanov invariant. Khavanov invariant, it is also something. It is some polynomial also, but it depending in extra variable t, and if t is 0, then it gives us this. And Gorsky statement, it is, first of all, it is good to formulate it in full detail, so what he's saying. First of all, in general, if in this case, it is also possible to formulate, but it seems very complicated or not, but at least I cannot do it right now. And Gorsky also in his paper, considering the case when one of these parameters m go to infinity. And in this case, situation become simpler, yes, and first of all, this variable, this things, it is p and m of q when m go to infinity. This is what? It is up to some shift of q, q to q inverse and some power of q. So what we have to do? M go to infinity, but n is still something. We have to take c x0, x1, x2, xn minus 1. I think maybe it is n or n minus 1. And then we have to factorize it by relations, and this again depends how we count it. But in one choice, x0 square, x0, x1, and the sum of x alpha, x beta, alpha plus beta equal s. But s is running from 0, 1, 2, I think till n minus 1. Maybe n minus 2, no, I think n minus 1. Yes. And we have to take such quotient and then take, no, this is quotient. Now, first of all, what we have? We have polynomial algebra in n minus 1 variables, and I factorize it by n relations. Now, in some sense, it is natural from our point, but from the point of pure algebra, this sequence is not regular. And so we have n elements, but even for simplest case, if n is small, the quotient is infinite dimensional. But infinite dimensional or not, but it has even two grading. Like it has z grading and q grading, like in all cases what I'm considering. But z grading, let us forget. But q grading we can take, and it gives us some series p m, maybe like that. And he first of all he claimed that it will be really the limit of invariant of link for m go to infinity. No, to be honest, I confused a little bit because there are two possibilities. We can start x0 square, x0, x1, or here we can start with that case, xn minus 1 square, xn minus 1, xn minus 2, and so on. And what is really pure if we just take usual John's polynomial and go to a limit, I do not know. But I think that this is correct. But maybe I confuse. And it is opposite, but it is not big deal. It means that we take q to q inverse and shift a little bit. It is not a serious change, but at least this is algebraically, this is description of invariant of a link, and then No, next story, which is good to mention because this fact is relatively simple, and it follows by many ways from this John's business and so on. But if we go to Havanov business, then we need something with T. And a real statement, maybe, I do not know, 6 years ago it was conjecture, but now maybe not. But statement is the following. We have to take C, a little bit bigger number, C x0, x1, x2, and so on, xn minus 1. But we have to add odd variables, xi0, xi1, and so on, xin minus 1. To that, and after that, let us introduce here the differential q. Yes, and this differential q, no, q is differential, and it is odd operator. Square of this will be 0, and it determined by which way. So it is graded algebra, and this is odd vector field, and to xi it is 0, and q to xij, it is a sum of x alpha, x beta, alpha plus beta equal j. Yes, and such kind of q gives me differential. No, it is evident that q square is 0, and so we have some complex after that. And a relationship with such kind of construction is clear, because what is this complex? We have x0, x1, x2, xn. This is degree 0, no xi. Then we have the summation xi times c x0, x1, and so on, xn, plus so on. And the differential is acting like this. And surely image of this is just ideal generated by this element. Therefore, homology of this complex here will be just this. And then if we calculate, no, we can take homology, and after that calculate the graded Euler characteristics. So we have homology here, H0, maybe better here, H1 here, H2 here, and so on. Yes, and the statement is that the Havanov invariant is character of this. It is just Gilbert polynomial, something depending in Q. Maybe minus here. Plus or minus does not matter. Let us put T here, character of this. T square here, character of this, and so on. Actually, this is the answer. Yes, and no, relationship with Havanov is also important, but even without Havanov and things like that, it is not. It is an interesting mathematical problem. In this case, surely, in this special case, it is known, and the answer even formulated in Gorsky paper, but it is not the only case that. But at least, how to say, the question from the usual algebraic commutative algebra point of view, if these are regular system, then homology exists only in degree 0. But it is not a regular system. Therefore, we have homology in many degrees. And because of that, this Chavanov type invariant is some non-trivial things. But I want to say, no, let us return to this. So, but what is this? If we take no, how many? Maybe it is like this. So no, I want to say that if we take fusion C2 times C2 times C2, maybe n times, or n minus 1 times Cm, where this is m-dimensional representation, and if we send m to infinity, then the character of this fusion things will be something like that. Maybe, no, I think it is correct, or almost correct, but the message is that Chavanov invariant is can be understood as a character of some fusion in this simplest SL2 case. Yes, but no, usually you can ask me a question and I can ask it by myself, that John's invariant, for example, of toric link has interpretation in terms of fusion of some representation. Of SL2, it is definitely true, but I do not know the precise statement, what is correct. But it is some character of something like that. And, but limit, if appear in this case, it is appear by such kind of construction. Now, to end what I talking today, I want to also explain some. Well, let us consider the again the situation E square, and let us take my representation W0. And this representation is, again, let me draw the same picture E0, then E minus 2 here, here E2 here, and so on. Let us take this vector and let us consider the subspace in this representation which generate by E. No, this is just, so again, no, it is just even. And W0, my notation was, yes, so it is tail starting in this, and what generate by this vector, in my notation, it was W0. So it is C, E minus 2, E minus 3, and so on. And I factorize it by e minus 2 square. Yes, and so this is W0, and if you it has two grading. It has Z grading and it has Q grading. And let me write, or maybe just write again, the character of this space. Now, the character of this space is what? I have start 1 plus Z, and how I write the character. So Z part is in E minus 2, E minus 3, and so on. It has Z degree 1. So it is Z, but here I have to put Q square. And Q square is a degree of E minus 2b, but because I have E minus 2, E minus 3, and so on, it is like this. Yes, and if you considering next, so next is what? You have this, then E minus 2, E minus 4. So it is Z square, Q6. This is the weight of the vector. Q square is degree of this, and Q minus 4 is degree of this. So it is Q6 over 1 minus Q, 1 minus Q square. And then it is plus so on, and generic term is Z power I, and I have to put here Q I times I plus 1, and here it will be 1 minus Q, 1 minus Q square, and 1 minus Qi. And this is the character of this part, which is chi depending in Z and Q. No, and no, this thing is good because, and interesting because of two reasons. One reason is following. If I have put here chi 1q, then the corresponding things is the left-hand side of Rogers-Ramanujan identity. Yes, and also, if you want to prove Rogers-Ramanujan identity, for example, then if you follow the way which I explained, that this kind of things, it count the configuration starting with -2 and so on. For that, I had some formula which follow from this Brion business. And if in this Brion business, if you write this formula and substitute z equal 1, then actually you get Rogers-Ramanujan identity, because if you, in this summation over the vertices you will get something, but it can be easy to rewrite it using Jacobi identity, and you get Rogers-Ramanujan as it is. Yes, and the other things that if you take this, then such kind of object will be, first of all, modular form. No, in general, if you have this formula with z, it is not modular form, and it is if q is exponent pi I tau, if tau goes to like this, if you have Z, no good transformation property, but if Z is 1, then it is much more nicer. Yes. And second thing, that this kind of character is a character of irreducible representation of Virasoro for irreducible representation of Virasoro. They are labeled by two numbers, and so this is irreducible representation of Virasoro for two type case. And this is just, if you're considering this, it will be representation of vacuum. It is character of vacuum representation of Virasoro. Yes. And one more the question which is now related with the question of characters of four-dimensional manifold. This is the question how to see Virasoro in this construction. Yes, and one extra story is the following. Well, I can take my space W even, and in this space I can considering the following things. Well, I said that I can write the one-dimensional lattice, and my configuration is crosses, well, they, which in this case stabilize to the even tail. Yes, and in this case, so what is this? I can take tail starting with 0, 2, 4, 6, and so on. I just fix this tail, and because I have 0 here, then all starting with 2. And what I calculate by this way is just configuration starting with -2, and which are going on there, and these things is coincide with the character of 2, 5. But because it is like that, what I can do, I can take all space from the point of view of configuration. I can take my space and my space of configuration, and I can study by which way. I mean all space. No, because our condition is Fibonacci condition. Then the question is, if we have nothing here, then corresponding part of a story is what? That we have nothing here, but now something is living here, and something is living here. And they are not relate to each other. So this part of a character is a product of what is going on here and what is going on here. Or in this point I have a cross. In this case, this cross forbid cross here and cross here. But after that, our story is living either here or here. As a result, we have the formula that the character of W even is a sum of two things. In the point 0 is 0, in the point 0 is cross. Each term is the product of two characters. So by this way, we have such kind of, we can calculate what is going on there, and it is some formula like that. But in this case, it is not big deal to study what is going on here. Therefore, for example, in a case when we have cross here, here is something which I wrote here, which can be identified with the character of Virasoro algebra. And also it is something which is living here. This can be identified also with the character of Virasoro algebra by the data 3/5. And if it is 0 here, then here also will be character of Virasoro, but different one. And here will be the character of Virasoro of different one. Yes, and then, no, it is time to stop, I think, now. But this construction gives you the interesting statement that the character of space of semi-infinite forms can be written by this way. Yes, and at least for me, it is it was the beginning of thinking about coupling of vertex operator algebra. I knew before that, but the fact that such kind of coupling is hidden here is follow from this combinatorics. And this is what, again, very interesting things. Maybe I'll try to explain something about this tomorrow. But the point, again, is that SL2 hat representation of level 1 can be constructed through Virasoro 2.5 and 3.5 minimal models. And no, I didn't explain about minimal models, and I cannot say much, but at least I will say something about this tomorrow. And it gives us something which is good, and even in combinatorics it has some generalization and also many open questions.